Okay, Algebra 2 skills number 1, simplifying square roots, and we're going to keep these without variables. So looking at our first example here, we have the square root of 20. So there's two different methods of doing this. One method will be to look for the largest perfect square that goes into 20. So perfect squares would be 2 times 2, which is 4, or 3 times 3, which is 9, and so forth. So 4, 9, 16, 25. Well, the largest of those numbers that go into 20 would be 4. So you can split it up like this. The square root of 4 in red there is the largest perfect square that goes into 20, and it goes into 20 5 times. We could then evaluate the square root of 4 to get 2. So notice that the 2 now has no square root around it because you evaluated that. Notice also that the 5, still in yellow, has no perfect squares larger than 1 that goes into it. So 2 root 5 would be complete. There's an alternative way of doing this problem that involves a factor tree. I will only do the factor tree for this example, but some may like it better. So what you may choose to do is to take the square root of 20 and break it into its prime factors. 2 times 2 times 5. Notice that the 2 comes in a pair. That pair, which is in red, can come to the outside written once, while the 5, written in yellow, is not part of a pair, so it stays on the inside. So notice this is the same answer to our previous problem. We also have the imaginary unit in Algebra 2, which will show up. The imaginary unit we denote with the letter I, and it's equivalent to the square root of -1. So you'll see some examples that have a negative under the radical. To break that up, we're going to take the largest perfect square that goes into 45. Again, perfect squares are 4, 9, 16, 25, which is 2 times 2, 3 times 3, and so forth. You'll find 9 to be that largest perfect square. So notice the breakup here. In red, we have the largest perfect square, which is 9. In blue, we have the square root of -1. And in yellow, we have just what's left, the 5. So the blue part is necessary to be able to continue here. Ordinarily, you can't take the square root of a negative because there is no number when multiplied times itself makes a negative. But if we allow I to equal the square root of -1, that allows us to evaluate this problem. The square root of 9 is 3. Notice again there's no radical. The square root of -1 we call I, and 5 is just what's left. That's under the radical. So 3i root 5 is the way we like to present our answer. Note that a calculator would not tell you this. It would just say domain error. So you have to know to take the I out. For a third and final example, I've got a side-by-side comparison of the square root of 72. There's often a common mistake here if you choose to take the largest perfect square out. And that mistake would be to take a perfect square but not the largest perfect square out. So on the left-hand side, I'm going to show you a method which is not ideal. That is, what if you chose to just take 4, which is clearly goes into 72 18 times, but 4 is not the largest perfect square to go in there. And the way I can tell that is that 18 still has a 9 in it. Remember, 9 is also a perfect square. So this is not complete because there's still a 9 in the 18. So I'd have to then take out the 9. As you can see, 9 times 2 is 18. The square root of 9 would be 3. And then finally, I get 2 times 3 to be 6. On the right-hand side, I'm going to show you a much more efficient way. And that would be if you chose to take the largest perfect square. So if you see a list of perfect squares, I recommend you go backwards in the list to find the perfect square instead of just always starting with 4. 36 is a perfect square which happens to go into 72. It goes in there 2 times. And the square root of 36 is 6. So notice we get to our answer right away. And you can tell this is the answer because what's left in yellow there, the radicand, does not have a perfect square in it. So always look for the largest perfect square when you use this method. So that's simplifying square roots.